We already talked about what a cell membrane looks like, and we talked about its job, right? And its job is to allow things in and out of the cell. It controls what gets in and out. As we talked about before, cells have a very high demand on oxygen. They need to have water. They need nutrients like amino acids. They need sugar so they can go through the process of making energy. They also need to get rid of things like carbon dioxide and waste, and that all has to happen through the cell membrane. And things travel in and out of cells a couple different ways, and that's what we're going to be talking about today. And we're going to first focus on a solution and what's happening inside of a solution, and then we're going to talk about what happens when particles move in a solution. So let's get started. So essentially, water and life go hand in hand, right? If I'm looking for life on another planet, the first thing I look for is the presence of water, because we know that on our planet, life started in water, and all life needs water. We're made up of like 70% water, and it doesn't take much. If you've ever been dehydrated before, you know it feels terrible, and it doesn't take a lot to get dehydrated. All you need to do is exert yourself at a certain level without enough water in your system, and you will become dehydrated very easily. So all cells have to be in a liquid environment in order to survive, and that's because particles move through a liquid. So let's talk a little bit more about that. Now, we talked about this before. This is actually a little bit of a review, but the term solution is when you have a mixture of two or more substances. So, for example, I wouldn't consider if I took a bunch of marbles of different colors and sizes a solution, because they're not really mixed together. You can separate them apart very easily. However, if I dissolve if I dissolve salt into water, that is a solution because they are now mixed together. You can't separate them out unless you evaporate the water and then you leave the salt behind. But for the most part, they're together. So when you have a solution, you're always going to have a mixture of two or more substances. And we have a name for those, the solute and the solvent. And we've talked about this before when we said that water is the universal solvent. It's always the solvent. But the solute is the substance that dissolves into the solvent, and then the solvent is the substance that does the dissolving. So for example, iced tea mix is the solute, water is the solvent. So just in this little image here, this will just give you that idea here. You can see I drew little blue dots represent water, little red dots represent the sugar. The water would be the solvent, the sugar would be the solute because it's being added. And if you add more sugar, it's going to be sweeter, obviously. You're going to have a higher solute concentration. And if you add more water, you're going to have a higher solvent concentration. So solute is what gets dissolved into the solvent. Okay, a little more about diffusion. So here's the thing about particles. They're always moving, right? They're always vibrating a little bit. So even your desk, right? If you're sitting in a desk right now and if you touch your desk, it doesn't feel like it's moving. It's solid. But if you were to look at it at the atomic level, what you would see is these little particles are actually vibrating. They're moving. And if you were to, let's say, light that desk on fire, it would burn up, right? And those particles would move fast enough that they would break their bonds and they would start to separate. So particles are always moving. And some things make them move faster, right? For example, temperature. If you heat something up, those particles are going to start to move a little bit faster. If you cool it down, they're going to slow down. And that's something that occurs in a solution. So what ends up happening is particles are always going to move from an area where there's more of them to an area where there's less of them. And that is a term we call concentration. So the concentration of something is how much of the stuff there is there, right? So for example, if there's if you're looking around your bedroom right now and there's just you in there, not a whole lot of people in there. But let's say everybody you knew in your entire life crammed into that bedroom. Well, now it's going to get pretty uncomfortable, right? That would be a higher concentration of people. So concentration is just how much stuff there is. Things always move from high to low concentration unless they're being acted upon by something else. That is what diffusion is. That's all it is. So let me give you another example. So if I take a look here at my little drawing down here, what I have is, imagine I have two rooms, right? And I have this little purple dot here represents a particle. Well, this particle is always going to be moving. So if I just leave it by itself, it's going to just be bouncing around here. It's going to be moving around. Let's say I heat it up. It's going to move around faster. And eventually what's going to happen is it's going to bounce out of the room. Now, this is not a particle that knows what it's doing. That was not an intentional thing that particle did. It just happened because of random chance, right? If it's bouncing around, eventually it's going to hit the right angle and it's going to bounce out of there. Well, now let's say I add a whole bunch of these dots, right? Now we have a whole bunch of them. Well, now when they bump into each other, it's going to be a lot crazier motion, right? So these particles are now going to start bouncing around. They're going to bounce into each other, and you're going to start to see these particles bouncing out of that room, right? So they're going to bounce out into the other room just randomly, right? It's random, but because they're so concentrated, they're bumping into each other more. Imagine, like I said, let's go back to my analogy of your bedroom, right? If you're in there by yourself, you can wander around in circles all day, not bump into anybody, and not have any problems. But now let's say you have 50 people in your room. Every time you turn around, you're going to bump into somebody, and then they're going to bump into somebody, right? Imagine bumper cars. One person hits somebody, they hit somebody else, and eventually they're going to get bumped out of the room. And that's going to keep happening until they end up separating out into the two different types of rooms. So diffusion is very simply the idea that particles are always going to move from an area of high concentration to an area of low concentration. And another example would be, let's say I sprayed some, let's say we're in the classroom right now, and I sprayed some cologne in the front of Axe body spray. You've all smelled Axe body spray before, right? And I spray some Axe body spray up where I'm sitting. Eventually, the people in the back of the room are going to smell it because those particles are going to spread out over time, and they're going to diffuse to where there's not as many particles. So it's very concentrated where I am, and then over time, it's going to spread to a different part of the room. There's a name for that. It's called the concentration gradient, right? So the concentration gradient is the idea that things always move that direction, from high concentration to low concentration. And that happens, it doesn't need to expend any energy to do that, because this is just random motion. They're just bumping into each other. This is just an image that shows essentially the drawing that I drew a moment ago, but you can see if this is the starting point, all these little particles here are going to be bouncing into each other, and they're going to be pushing the particles through this membrane here to the other side. So what does this semi-permeable membrane represent? It represents the cell membrane, right? So the cell membrane allows things in and out as well, and over time what you're going to see is eventually you're going to have a scenario where all of these little particles have separated because of diffusion. And at this point, there's equal amounts on both sides. So they're going to keep moving back and forth until they hit this point called equilibrium. And that's what I'm going to finish up with today. Equilibrium is essentially the idea that particles are going to continue to move from high to low concentration until they equal each other, until they have the same amount. And that makes sense, right? If there's 100 people in one room and 50, well, let me go back to my drawing here just to. So let's say I have 100 people in this room, right? And I have 0 people in this room. Well, what's going to end up happening is they're going to bump into each other, and eventually you're going to have a scenario where, let's say now I have 40 people in this room and 60 in this room. Well, now there's more on this side, so they're going to move back and forth, and that's going to keep happening until we hit a point where they both have equal amounts. And when they both have equal amounts, there's nowhere else to go. So they're just going to stay at, we call that equilibrium. And all things in nature are moving towards equilibrium. And a lot of our body systems, a lot of the way our body works is actually preventing equilibrium from happening, because equilibrium stops the system from doing something. But we'll talk more about that later. We're going to just finish up here today with just one more quick idea. Now, we just talked about this concept of diffusion, right? Particles are always going from high concentration to low concentration through a membrane. That's what diffusion is. It's a simple idea, right? Now, does that take energy, right? Does it take energy to move things from high to low concentration? Well, in a normal situation, the answer to that question is no, it doesn't actually. It doesn't require energy because these particles are moving randomly. This is random movement. They're not thinking, they're not deciding where they go. They're not saying, oh, I want to go to that room because there's too many particles in this room. They're just moving around. And the more particles that are there, the more they're going to bump into each other, and they're going to move quicker, and they're going to move out of the room faster until there's equal numbers and we have equilibrium. So even though they're moving, and even though they're going from high to low concentration, this does not require energy. And there's a term for that. It's called passive diffusion. So this is considered simple diffusion. It's called passive because it doesn't require energy. Perfect scenario, think about it this way. You're tubing down a river, right? You go down to the river, you jump in a tube, you sit there, and you just cruise down the river. You don't have to kick your feet. You don't have to swim. The reason why is because the movement of the water, the current is pulling you down. Think of the movement from high to low concentration as the current of a river. And these particles are just little particles sitting in inner tubes enjoying the ride. They don't have to work against it. Now, if I wanted to go from low to high concentration, that's a different story. That will take energy. And that's what we're going to talk about in the next lecture. Thank you.